Alright, so today I'm gonna be explaining the problem that Mr. Pabico handed out in class today. So basically, we can see it's a mass swinging around on a pendulum, then it gets cut at this point, and then it basically falls to the ground in a uniform arc, I guess, or whatever you want to call it. So how we start to solve this problem is we first want to find the velocity it has right here, and then after that it just becomes kinematic. So I'm going to draw it red just to have everything. So you can see it's a 1 meter string, 0.72 kilogram mass, and it's 1.25 meters off the floor. So instantly we know we want to find this height, and we want to find this height, because basically here it will have, if we make an energy equation, mgh1, and then we have height 2, which is mgh2, but we also know, because this is a different angle, we can see 14 and 36, two different sizes. This one's smaller, so basically we know it's going to still be moving here. So we're going to also add our velocity and v squared. So how do we calculate the height? Well, it also says it's 1.25 meters above the floor, so if we say this is h equals 0, we know that this is going to be the cosine minus, or 1.25 minus the cosine of angle 1, and then that's going to be the cosine of angle 2, but then subtracted from 1.25. So we can say height 1 is equal to 1.25 minus the cosine. Cosine angle 1 is said to be 36 degrees, or 31.6. And then height 2 is equal to 1.25 minus cosine, again, 14.8 because it's angle 2.8. So now that we have height 1 and height 2, we're going to shove it in the equation and solve for the velocity. So if we notice here, we have masses, and it gives us a mass, but that's actually unimportant to this problem because, as we can see, the masses all cancel. So then we're left with gh1 and gh2. So if we're solving for v, we'll get v equals the square root. This is after we algebra some stuff. It'll be g. I'm gonna just write no, I'll put in the values of h1. So h1 is 1.25 minus cosine 31.6, and then we're subtracting this one, so then we have minus height 2, which is g times height 2, which is again 1.25, minus cosine of 14.8. And so then all this again is multiplied by 2 because we're getting rid of the 1/2, so then it's times 2. So I'm gonna real quick plug that into a calculator, just a normal graphing calculator. Minus cosine of 31.6, and then minus, okay, hold on. Hardest part is plugging this all into a calculator. So 1.2 minus cosine 6, then minus 9.8 times 25 minus cosine 14.8. And I'll just shove a few parentheses and see if I have it. Crap, I put 1.2 instead of 1.25. Okay, you know what, I'm gonna just do this. 1.8. I don't know why I don't know how to use a calculator. Minus cosine 31.6. And then minus 8 times 1.25 minus cosine 14.8. Yeah, that's enough parentheses. And then times 2, and then square root. Okay, so then I get a value of velocity after plugging all that crap into my calculator of roughly 1.5 meters per second. It's like 1.501. So now what we're going to do is we notice that this velocity is there. So we're going to figure out what angle we have here. So this might be really confusing, but it's actually a lot stupider than you think. So this is basically going to be making a circle. So the tangent line from a flat thing will actually have the exact same curve here. So as hilarious as it seems, this launch angle is actually just going to be 14.8 degrees. So that's pretty funny. And our initial velocity is going to be 1.5 meters, and we know what height 2 is to find the initial position this way, because basically this arc would be going down here. Find the initial position over here. We're going to do, this is just sine of theta, basically, because the radius is 1. So basically, now I'm going to just shove this on the other side. Ooh, that is not a good curve. So it'll go a little bit lower, but basically we're starting up 1 minus, no, not 1 minus cosine, 1.25 minus cosine of 14.8, and then we're starting over by, what's it called? Nope, not cosine, sine of 14.8. So basically, if I plug this into my calculator just to make it easier for us, 14.8, and then 1.25 minus cosine 14.8, we get, I'll just say 0.26 and 0.28, and that's going to be in meters. So then we know we have an initial velocity of 1.5 meters per second, and our initial launch angle is going to be 14.8. So we can break this up into two components. Our, that's not upwards, our sine component and our cosine. So it's going to be sine 1.5 sine 14.8 for the initial velocity. I'll just say VO sine theta, and then VO cosine theta. Those are our two angles, and so basically we're going to set up our kinematic equations now. So the change in y is going to equal basically 0, because it's going to be, or sorry, not change in y. The final y position is going to be 0 if this is our reference point. So we can just say 0. Our initial y position is going to be up 0.28 meters, so 0.28. And then we still have our initial velocity in the y direction, which is VO sine theta, and then minus 1/2 AT squared, which is just multiplied by time, 4.9 t squared. So now that we know all these values, so what I'm going to do is I'm going to just figure out what VO sine theta is, I guess. 2.8. VO sine theta is 0.38. I'll just say that. We plug it into quadratic formula, and we're going to get, so negative 4.9, 0.38, and 0.28. So for our value of time, we're going to get t equals 0.28. And so now I'm going to set up the final x position graph, which is going to be, I'll just say, change in x, probably, sure, I'll say change in x. So if we're starting here, you know, I'll just say actually that we're starting here, and this is x equals 0. So then we have the x final, which I'll just say x is equal to x initial, which is going to be 0.26, plus VO cosine theta times RT, which is 0.28, and it's not accelerating because it doesn't accelerate in x direction, no air resistance. Don't have to worry about that. So when we plug this all into a calculator, 0.26 plus 1.5 cosine of 14.8 times 0.28, we get a value of 0.66 meters for the total distance traveled from this point, which is what the question is asking. So that's going to be your final answer. And it says calculate the horizontal distance from here, where the point lands, and that is 0.66 meters. So just for reference, I'm going to check how long that took. That was 10 minutes. So now I'm going to just go into a little bit more details explaining a few of the steps. So to find the original heights, basically we were just using cosine, because basically we were trying to find this. We know the total height from here to the ground, specified as 1.25, and then we're just going to subtract this portion to see the two heights. Then we just set up our energy equation here by basically just saying that it's going to start with no velocity, and then it's going to end with some velocity but less height. And we just plugged in our values of that and solved for v. Simple algebra, we got a value of v equals 1.5 meters per second. So then after that, this is the only difficult part of the problem. So assume this goes in a circle, the line that's tangent, and then just flat. That'll be 14.8 degrees for the initial launch angle. Really weird. I don't actually know why it's that, but it probably is. So yeah. And then after that, we just set up our equation with just two-dimensional kinematics showing the 14.8. And so it has an initial velocity. We broke it up into VO sine, VO cosine, and we made two equations. This equation is for the y direction. This equation is for the x. I just put 0 as the initial y, or final y, because it's landing on the ground. We have a x because that's what we're trying to solve for, the final x position, which is over here. And so then we just plugged in our values. We solve for t. You can also technically like solve this equation for t and then plug it in there, but then that just turns into a whole mess that I don't really think is that necessary. But yeah, so that's basically it. Yeah, this problem's, I feel like, pretty easy for one of the test things, but yeah, thank you.